mean, I'm having a headache, I don't know due to what, but it would be some chemical imbalance in my body. So I'm measuring that system, but quite often we don't know what we are measuring. Right? The body kind of knows it's not good for me to survive. So the reason why we are thinking beyond classical sensors is to ascertain the ability for it not only to work as human, but to as a supportive to human beings. As a nose, a lot of research work has gone in making electronic nose. And I have been hearing this word electronic nose ever since I was a bachelor's, or ever since I was a school student. And we still don't have one which is formulated yet. Okay. We still do not, an electronic nose doesn't necessarily mean something which measures smell. Because quite frankly, smell is a kind of weak sensor. People who do research on smell will not agree to it. But think of it this way. You go to a very smelly, you have a very nice smelling flower. After a minute, your nose adjusts to it and you don't feel it. Right? Or if you go to a pungent room, or if you smell it for the first time, but we very soon adapt to it. Compared to everything else, that adaptation is the quickest. So, and we are not as good as, say, our other counterparts in animal world. I mean, dogs can have much better smelling abilities than we do. So this looks like it's one of those sensory things which we are losing with time. Agreed? So if I can ask my girls, students, have you tried putting flour on your hair? Does it continue to smell for the rest of the time while you are wearing it? So brain basically says, yes, it's there, I know it was good, I don't need to know anymore. Agreed? Can we just pause for a minute? Just pause for 1 minute. So electronic nose, this is why there has been a lot of work which has gone into building electronic nose, but we still are far away from that. The other thing which has happened is reproduction. With camera work, we can reproduce an image. Right? But the vice versa has been a bit tricky. So our temperature sensor, which we saw in the morning, would be equivalent to our skin, which we have. And skin is a very good sensor. In another way, it's a distributed temperature sensor. Okay, this is an experiment that would be worth doing. Oh no, we do that. Sometimes our legs are in cold water and we feel that. And even though the rest of the body is in hot, so we can do differential measurement as well. Okay? So it's a distributed differential sensor. So and it's an array kind sensor. It doesn't have very high sensitivity, but it does a fairly good job of telling us where we are. Now we'll be looking at a different type of temperature sensor. So till now, we were recording the outside world. How is my heat? How is my other things? So kind of sensor we have looked till now is eyes, hands, weight, force, pressure, and the distributed kind of things. Now we will try to look at my inside. How hot my body is getting from inside. Okay? Particularly when we make chips, how hot they are going to be. And this becomes fairly relevant whenever because we are operating our chips at higher and higher clock frequency, which means they are producing more and more heat. Many of the chips would have got inbuilt thermal management, wherein as soon as they get beyond a certain heat, they are brought down to, they are shut down. Okay? So actually, I wanted to show you guys a video. I know videos don't come very well on the presentation, but it will be a YouTube which will show you as to what happens when we don't monitor heat properly. Maybe we'll do it at the end of this thing. So we are either measuring the ambient temperature, which we have been doing till now, how the world is around us, or we will be measuring the on-the-chip sensor. Now for both of these applications, now any sensor which goes on the chip, ideally it will be good if you don't bring a new material on a new type of device. It will be good if you measure something which we already have. And we said initially that diode is a fairly good temperature sensor. Now, all of you guys know about diode operation. So, this is the sum of the maths which I will not be doing, you will be doing on your piece of paper. So, diode is what we call it's a CTAT, in the sense that voltage is conversely proportional to absolute temperature. It's not measuring 27 degrees Celsius, but it's measuring the temperature scale in Kelvin. And this is generally of the order of 1.5 millivolt per Kelvin. So, for every Kelvin, that is the temperature coefficient of diode, and it's negative. Now, if diode can be used as a temperature sensor, so can the base emitter junction of a transistor be. So, you have done the bipolar transistor in your courses. The base emitter junction is kinda a diode. Right? It's a PN junction or an NP junction, depending on what kind of transistor you have. So, that can be also used as a temperature sensor, and that will also have a negative temperature coefficient. So, for those of you who had forgotten, that was the relationship between the simple diode. Okay. Now, I have shown here, you are right, there should be Vt should be Kb by Q kBt, Kq by T. And we can see the drain current of the diode current would have an exponential relationship with temperature, provided that was the only relationship with temperature. The IS, the saturation current, or the I naught current, the current which flows when my voltage is same as my drift voltage, that has a fairly complex relationship with temperature. It has something like this. If you look at IS, that has got a relationship based on my number of dopants, Pn and Np. It has got based on their diffusivity, Dp and Dn, and it has got a relationship between the length by which an electron hole pair survives on its own, because after some time it will recombine. Right. So, if I have formed a hole, it has a finite lifetime after which it will recombine. So, on average we take all of these things, we will have it there. Now, you might recall semiconductor has intrinsic concentration or intrinsic number of charge carriers, which is Ni. From there you can find number of holes and number of electrons. The intrinsic concentration Ni already has a, where is my display or the stick? There is no stick here. Okay, no worries. So, you can see here, look at the line just below, above Eg is the band gap. Your Ni has got a very funny relationship with temperature. It has got a T cube and it has got an E relationship as well. Now, Eg is your band gap. That's, well, you can assume it to be constant. Right? So, as a relationship, we get an Is which becomes a fairly funnily relationship to T to the power a number which is not nice number. But we can write, if you're just thinking in terms of temperature, the second last equation could be your Is relationship. Okay. Now, think of diode. What are we measuring? If we give a fixed diode current, we like to measure the diode voltage. So, diode voltage will come from the first relationship, first equation, and Is has got a temperature dependence and the first relationship has a temperature dependence. Now, for the next couple of minutes, could you guys try to come up with a relationship between Vd and temperature? So, essentially we are fitting the Is equation in the first equation and then rearranging the equation to get a relationship between Vd and temperature. Could we give that a shot? See how it works? So, first thing first will be, if I do a logarithm on both sides, Vd will come out of exponent. Okay? So, let us try it for a few minutes and see how it goes. Now this should be fairly simple maths. Now some of you require an examination. Who are these people? I've been told there has to be an examination for some of you. Is anyone expecting grades from this course? No? Yes, no? Because for that we need to set an examination paper. If none of you expect a grade, then I don't have to set a paper. Right? My life becomes easy. So is anyone expecting grades or credits from this course? Okay. If anyone is and is shy to talk out, any examination which I organize is generally an open book examination. So you will have all the lecture material at hand. And now 5 people would like to write that exam, right? So if some of you would have proceeded down these lines, wherein you would have, there's an e to the power q eg minus qt here, and on that term we have e to the power vd minus n phi t. If you would have expanded, you could get an equation something like this. If you look at the top expression, it would get something like this. Okay? Now that is still not a very nice relationship, is it? It has got temperature in the second term. It has got T log T in the second term. In the third term, it has got T. In the fourth term, it has got another log of IST by I, which is not a nice relationship. If you're going to use it as a temperature sensor, it's a fairly complex relationship. One can then think of, okay, what if I have a voltage measured as a reference temperature? So that's the voltage which is response at absolute temperature T. So if I take another voltage, which we will call as, say, V of TR, this value, which I have measured at a known temperature, then I can place it back in this relationship and try to get an even more complex relationship here. Okay, I can do an expansion like this. Agreed? And then, of course, we will do the favorite thing which we do in electronic engineering. Anything which has got a much higher complex term, we can do. So now if we ignore some of the higher order terms and then take a ratio of how is this voltage changing with temperature, we can come with a much nicer, simpler expression of the voltage coefficient with temperature. So essentially, Oh, oopsie daisy. Where is my mouse? So this term will disappear if you take the derivative, because they are all constants. There is Ag and there is NKTR by Q. So TR is the reference voltage at which we have measured. Everything else is constant. So that term will disappear. Here there is just a function of T. So dV by T will just be this term. Agreed? And similar, here we will get T, here we will get nothing. That will expand, but we can assume that there will be many higher order terms here. Some of those higher order terms we can ignore, my apologies. And similarly in these relations, if we do ignore higher order terms, we get a fairly nice relationship of dV by dt, provided we know a reference voltage at a reference temperature at which we have measured our voltage. And this comes out to be somewhere in between minus 1.2 to minus 2.2 millivolt per Kelvin. Now, if you look at these are diode characteristic curves. You should be able to appreciate the upward going curve. If we look at these curves at different temperature, you can see, my mouse is behaving. So I can't see my mouse on my computer, so I have to keep on turning my head. You can see various characteristic curves at different temperature profiles. Now, a simple diode can be used if you are having a low forward current as a temperature sensor. It can be used, but you need to worry about avoiding self-heating, because in forward bias, the current exponentially rises very, very quickly. So if it rises too quickly, it will self-heat the diode, and if it self-heats the diode, it produces more electron-hole pair, which then produces further current. Now, this could possibly be used to measure ranges of minus 100 to 250 degrees Celsius. Most chips are not designed in that temperature range. So do you know what temperature range commercial circuits are designed for? What is that range? Minus 40 to 120. Are you designing for military? That's why he knows that temperature range. That's that military range of scales, right? Commercial chips aren't designed for that extreme. Where do we get 120 degree for our commercial systems? So we design chips only till 70 degrees Celsius. Okay. Then there is an industrial unit which goes slightly more range. The military range is bigger. Okay. So this goes to suggest that an on-chip sensor, on-chip diode type sensor, provided we are going to use it for commercial and industrial application, should be good enough for these sensory application. Now, we also said you could use a BJT in making a commercial sensor, a temperature sensor. Now, BJTs don't exist in a CMOS process, because we would have made a chip with just N-type diffusion in a P-type substrate. Okay. Remember the other day we saw how a chip is made in a CMOS process. But BJTs do exist as parasitic elements here. So if I can stand now, so if you can look here, if we create a P-type transistor in an N-well, I would have created an N-well, I would have deposited some P plus. But if I make a structure like this, I put a P plus here, N plus here, and P plus here in an N-well, I'm not trying to make a transistor, but I am getting a parasitic transistor here. This is a horizontal parasitic transistor. If you think of this structure, there is P plus here. If I take this N-well from N plus and then take this P plus from the substrate, then I have got a vertical parasitic transistor. Agreed? So BJTs do come across as a parasitic structures in CMOS processes. Now that's good, because if I have parasitic such devices, I could use them for temperature monitoring. Now here is a fairly simple sensor which tries to monitor temperature. Now we said if we apply the same current the voltage changes in a diode as the temperature changes. Agreed? So, if you look at the left hand side of this circuit, so essentially if I fix the current flowing here, or let us fix the current flowing here by these current mirrors. So, how the PMOS is, if the second years do not understand, that is perfectly fine. This voltage, I mean here the base and emitter is shorted, so it is a collector base junction. This voltage should be dependent on temperature. Now, this is a current mirror circuitry wherein we have got two NMOS's current mirror below that. This also means that this voltage should be the same as this voltage reference here. Right? Oh, my apology, my brain is dead. This will then change to the currents which are flowing here, and that we then allow a current to flow through a resistor, the reference volt, that will give me a voltage which has got a negative temperature coefficient, and will give the voltage as measured across the resistor will give me a temperature sensing capabilities. My brain is dead. You can see I am slurping. The moment I start slurping, I know I have lost my ability to teach. Should we take a lunch break, earlier lunch break, guys? Okay, and then finish it after the lesson, because I am tired now. My apologies. I was hoping I would finish the temperature sensor now. What we will do after lunch break, we will finish the temperature sensor. We will do something about a pH sensor. These two sensors will certainly finish today. Okay, and I need some rest. Okay, so my sincere apologies for this, but let's do it. Meet after at around 2 o'clock today. Let's meet at 2. Okay, thank you. Uploading a set of tutorial problems and a set of tutorial solutions. Okay, so it will be available online for you to download whenever you want and for you to access them as well. The network is not proving very reliable right now, so what we will do is, rather than updating, so the tutorial problems are already there on the web page. No, sir. Okay. The solutions were not there. So now the solutions will be online. Okay. It's the same web page. If you have not written it, just write it down. That's where all the lecture notes are also there. I gave you a textbook, a book which you can download, which has collected chapters on other aspects. You can download it now. I will keep it running for about another month, and then I will take it out. Okay. So try to download before that time. Wait till today evening, because the solutions are taking some time to upload. As soon as they upload, you can download it. So by tomorrow morning, it should be perfect. The thing is, the NIT network is not working for me, so I have to use my phone network to upload, and that's not the fastest system to upload big files. Okay. Good. With that as the background, if you have taken a note of the web page. Okay. So I know I started excuse me, temperature sensors in the morning session. I'll come back to temperature sensors towards the end of this session. The plan would be we do actually, you know what? Let me finish the temperature sensors and then we'll come back to. Doesn't make any difference. So we derived the voltage coefficient of temperature in the morning. And then we realized that we can use a transistor as well as a bipolar junction transistor as a temperature sensor. So the plan of today is we are starting at around 2:50 and I will try to finish before 4 o'clock. Okay. I am aware that today is an important day for many young people. So I will let you go in peace so that you can buy your cauliflowers or whatever these you have to give gifts these days. And if you have to give a flower to your significant better, you should buy the biggest flower possible. The biggest flower market is the cauliflower, right? And it's good for health as well. You can eat it, make a salad, make a sabji. And the best part is cauliflower sticks in both North Indian cuisine as well as South Indian cuisine and European cuisine. So you can't do anything better than that. For those of you who know, who can read Hindi, on this day I will recommend you to read a very nice poem by Suryakant Tripathi Nirala, or just search Nirala. Right? So Nirala wrote a poem abusing the rose. Right? So the Nirala was a communist author, communist or socialist poet. So his whole poem is an abusive allegory from mushrooms. You know, mushrooms grow everywhere, where a rose needs so much care and protection. So the poem is from the mushrooms to the rose, right? Basically saying mushrooms are common people, everybody tramples on us, we are there, whereas rose, everyone takes care of it. So if you like Hindi, that's a very lovely poem which you can read about roses and why not to buy them. Okay, dokie. So we went with simple diodes, and then I said, okay, the diode voltage, we derived that the diode voltage here becomes a function of temperature. Okay? It's a function of absolute temperature there. And it will not be a great idea to measure it directly because of other effects. Whatever we are measuring the diode voltage, if it becomes part of rest of my electronic circuitry, the rest of my electronic circuitry could start influencing its action as well. So a simple solution to do that is a circuit something like this, which mirrors the currents. So the top two PMOS current sources mirror the current. So the current on two sides become the same. And if the current on two sides become the same, the Vref voltage on these two sides also become the same. Okay? So just like your Vref voltage on this side has a negative temperature coefficient, we know it falls with as the temperature goes up, the voltage starts falling down. Voltage on the other side also does the same thing, and that's why you can take a copy of it. However, this voltage has got a fairly complex relationship with temperature. We did all the analysis and we still found a fairly complex relationship with temperature. One of the reasons why we found a fairly complex relationship with the temperature, if you go back, was that IS, the reverse bias saturation current, that has a fairly complex relationship with temperature. Right? We had T to the cube, e to the power g, and so on and so forth. Okay? So a circuit which gets rid of this IS effect completely is to look at what if I make two of these devices. Total current would be 2 times these. Okay? If I have two such devices, each one of them giving a current in parallel, the current will get added. Agreed? So the current will be 2 times IS e to the power blah 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 blah. Or better still, if you look in the voltage terms, I will get 2 times all of this. Okay? Now, what happens when we let's go back to this circuit. So what happens when we subtract two numbers which are logarithmic of one another? Remember, we had these log t was appearing quite frequently. So how do we get rid of log t from an equation? So when two numbers we subtract log a minus log b, the result becomes log a divided by b. So if we have one source which is n times or 2 times the previous one, another source which is just as it is, if I subtract these two, because my current is in log domain, so say my voltage was A plus log of temperature, and the other one will become 2A plus 2 log of temperature. If I subtract these two, log t will cancel out one another. It doesn't make sense. Follow in this circuit. Ignore the circuit for the time being. So if I have one base emitter voltage which is n times, which has got n different gates in parallel, so I'll get a relationship Vt times log of n times I naught. Remember, I naught is being n times. The other will be just log of I naught time. If I take the difference of these two, then I naught will cancel out, Is will cancel out, all I will get is a Vt log of n. Now Vt was also temperature dependent, it was nQt by nKt by, it was Qt, my brain is still dead, Kt by Q, right? It was directly proportional to the temperature. So by doing a circuit like this, where we force, and we can do it two ways. We can either say we can make the transistor have n different transistors in parallel, or I feed an n times I current in that transistor. Okay? So current voltages similarly we can use. And then if we take the difference between the voltage in these two circuitry, the difference voltage, this difference voltage between these two, that will be absolutely proportional to temperature. It will not have those funny log of terms, it will not have those complex comparators. Okay? There are similar circuitries which are, rather than having n times the current, you can have n times the diodes sitting in parallel. So now the same current is flowing, it's a current mirror circuit, but you have n times the diodes in these two between. Okay? The other alternative which you can also do is, if you have looked at the current here, you can then mirror that current separately through a third device and then say the voltage across this resistance. Remember the first circuit which we saw when we just taken the voltage across the resistance. So we can have, okay, we have got n times device times divide there, and then we take the voltage across a resistance. So now we have got both the absolute the voltage which is proportional to the absolute temperature, as well as the voltage which is doing the other way around. Good. Rather than pouring you to more complex circuit, this is just a self-starting circuitry when we have got a startup circuit on one side to help it start rather than provide a current source of its own. So these circuits can help you measure the temperature of the chip on which you are working. Now this is another place where analog people will survive. The temperature sensor on the chip, even though you have a digital chip, the temperature sensor will always be an analog device. Okay. Good. Right. Let's talk to the last particular sensoring modality which I am going to cover before I hand you over to my esteemed professors who will teach you for the next few days. And that is chemical sensors. Okay. Now, chemistry